Let's try a few problems. Look up here for the premise, if you would, at the top of the screen. A population of MCAT scores, MCAT being the medical school entrance test, has a mean of 500 and a standard deviation of 100. Let's just take that for granted. We sample 9 people who have MCAT scores. What's the probability that the sample of n equals 9 will have a mean score of greater than 501.1 or greater? What's the probability that the sample of n equals 9 will have a mean score of 501.1 or greater, as indicated by that symbol? Probability of a mean greater than 501.1. Now, I've given the answer there in bold, but let's talk about how I got at it. Beneath it, you'll notice that I drew the distribution of sample means in blue. But once I did that, and what I haven't done is taken the care to draw all those capital M's. I mean, I can't do that every time, but you'll see that it's the same principle. And by the way, the distribution of sample means that's drawn in blue has the same mean as the population, just like before. Now, pardon me, what I did was, of course, calculated the standard error, which again literally is the standard deviation of the distribution of sample means, 11 over the square root of 9, and I get 3.67. Not the friendliest number. But then I'm ready to plug that into my Z formula. 501.1 minus 500 divided by 3.67, and I get 0.30. And therefore, I assign that sample mean. Now, again, what's embedded in that blue curve is sample means. That sample mean has a Z-score of 0.30. Now, if I go to my tables, I'll see that 0.30 has a tail value of 0.3821, and that's my answer. I've planted my flag. I know that 501.10 is to the right of 500. I know that 500 splits that whole curve, and therefore I'm looking for a tail value. And this is sort of a revisit of what we did in Chapter 6, of course. But again, what we're doing here is not talking about individual scores, but the probability that sample means will have a mean, a score of m equals 501.10 or greater, just as we were dealing with raw scores before, except I must translate everything instead of raw scores, translate them into sample means. And can I assign a z-score to a sample mean? Sure, that's what we're doing here. The first thing I have to do is calculate that standard error. And the next thing I have to do is assign a z-score to it. So once I do that, I can treat the blue curve, which is stacks of capital M's. That's what it is. It's stacks of capital M's. I can treat that blue curve precisely as it were a black curve of individual scores, of X's, as we represent individual scores. So now if you'll indulge me, can I go to the next example? Yes, I can. It's rhetorical. Here we go. I'm going to go over here. Look what I've done differently. Same population parameters. A population of MCAT scores has a mean of 500 and a standard deviation of 11. But look what I did. Did something nutty. We sampled not 9 people, but 256 people, holy cow, Batman, who have MCAT scores. What's the probability that this sample of 256 people, that's a lot, will have a mean score of 501.10 or greater? Well, it's an infinitesimal probability this time. It's much smaller. We went down from 0.38 to 0.06 roughly. How did I do that? Well, follow me on this, if you will. The first thing I must do is calculate my standard error, 11 over the square root of 256, which of course is 11 over 16, 0.69. So my standard error went from 3.67 to 2.69, a whole different thing. I'm sorry, excuse me, I said 2.69. It went from 3.67, pardon me, to 0.69, a much smaller number. And why is that? Well, because the sample size is so gigantic, we know that the distribution of sample means gets a lot skinnier. It gets a lot skinnier. And we also know that the standard error is going to get a lot smaller. In other words, those means are shoehorned in toward the middle, towards 500. Now, what's that do to the z-score? Well, it makes that mean of 501.10 a lot less likely. 501.10 minus 500 divided by 0.69, and I get 1.59. Now, if you go to your z-tables and you look at the the tail value rather, you see that tail value is 0.0559. Now, Let me just say this in passing. Before this, I want to draw a couple contrasts. Look at the difference that the way I drew the distribution of sample means in blue here. It's stouter. It's samples of only 9. Therefore, we could get some somewhat aberrant samples of 9. And therefore, the standard error isn't particularly small. Over here, I got samples of 256. We're assuming that those means will line up in the middle. They have to. And therefore, the standard error is a lot smaller because that curve is so skinny. Now, to leave one thought in passing, if you will, when the casual observer sees a mean of 501.10, doesn't that look close to 500? How could it be that we would be unlikely to get a sample mean greater than 501.10? Well, bear in mind what we're talking about here. We're not talking about individual scores. We're talking about sample means that are drawn from large samples, 256. Wouldn't we assume that a sample of 256 would look just a whole lot like the population? Of course we would. And therefore, it'd be unlikely to deviate much from the population mean. In fact, it'd be unlikely to deviate much at all, as this suggests.